In our discussion in the power electronics section, we are now going to look at a type of DC to DC converter, and just not ordinary DC to DC converter, but we are going to look at buck converter. What is actually a buck converter and why is it important in power electronics? Well, a DC to DC buck converter is a DC to DC converter circuit that steps down input voltage to a lower output voltage. And we already know that a DC signal is called a direct current or the direct voltage, and the waveform is seen such that the voltage and the current are constant with respect to the time, and we have the voltage, and in most cases the voltage is constant. We can say 10 volts, 20 volts, and etc. A basic description of a DC to DC converter is such that if we have the input to the circuit, we can have the input voltage, and if the input voltage is a DC such that we have 100 volts as an input, and now we have the DC to DC buck converter circuit. So a DC to DC buck converter circuit, from definition, it says it will step down the input voltage to a lower output voltage. So our output voltage, we can say we have 50 volts, and the input is DC and the output is DC, and we will see that in order to control how the value of the output voltage will decrease based on the input voltage, we normally have a control, and we have discussed this previously. And the control, to control the amount of how the input voltage will decrease in magnitude, is through the duty cycle. So controlling the duty cycle will correspond to the decrease at the output voltage with respect to the input voltage. In simple definition, we can quickly say that a DC to DC buck converter step down the input voltage to a lower output voltage. And in our discussion, as we have outlined, we are going to look at the circuit component. If you want to build a DC to DC buck converter, what type of materials or component is needed? And we are going to look at the circuit diagram or the circuit schematic, in which you can connect all these components to create a buck converter. And we will look at the circuit equation of a buck converter in terms of the on state and the off state. And we will look at the state space averaging model in a continuous conduction mode, and we will look at the generalized state space averaging model. And these two models is very important if we want to create a model based on the operation of the buck converter. Those equation becomes very important. And finally, we will derive a transfer function based on the model that we have discussed. In order to build a buck converter, firstly we need a component, and we call it the circuit components. And the first component we need is a MOSFET. And what is a MOSFET? A MOSFET is nothing but a switch that will turn on or off. And secondly, what we need is a diode. And this diode, as we've seen from some of our previous discussion about a diode, we know that the diode will allow current to flow in one direction, and we can say the function is to allow the current to flow in one direction. And thirdly, what we need is the inductor, and we know the function of the inductor. where it stores energy in its magnetic field. And fourth, what we need is a capacitor. So a capacitor can act as a battery, and it normally stores the energy. And we have the fifth is a resistor. So a resistor mostly limit the flow of current. So these are the components that we need, and we have described the description or the function of each of these components. If you have all these components, now it is easy for you to build a DC to DC buck converter. So I will now draw a circuit diagram of a DC to DC buck converter. The circuit diagram is such that we have the voltage input denoted by B in, and we have the MOSFET, and this MOSFET is connected to a diode, and this diode is now connected to the inductor, and we have the capacitor, and we have the resistor, and here we have the voltage output. And this is our MOSFET, this is our diode, this is our inductor symbol, this is our capacitor, and this is our resistor, and we have the voltage output. The important thing to realize is that the control signal, as we have mentioned, which is the duty cycle, will now be able to produce a PWM signal. The MOSFET is now going to operate on a PWM signal. And because of this PWM signal, it will now control the voltage output to be less than the voltage input. So if you have a connection of a circuit in this form, you are now already creating a DC to DC buck converter. We are now going to derive the equation that governs the operation of the DC to DC buck converter in a continuous conduction mode. And if we want to model this type of buck converter, we have to derive the equation. And this mathematical equation is mostly derived from the circuit itself. And we will go step by step into how we can derive this equation so that we can solve for the state space averaging and generalized state space averaging model of this buck converter. And in this discussion, before we derive the equation, we are going to look at how the buck converter operates. So we can say operation of DC to DC buck converter. And in this video, we are going to look at how this DC to DC converter operate in a continuous conduction mode, and sometimes they call it the CCM. So we can say in the continuous conduction mode, what really happened? We can say that the inductor current never drops to zero, and the converter itself operates with the periodic switching. In this continuous conduction mode, the important thing to remember is that the inductor current, that means the current that passes through the inductor, will never drop to zero, because this type of circuit an operation will have a continuous current flow through the inductor. That is why it is called a continuous conduction mode. And this type of current is denoted by the IL. So later we will be able to derive the equation such that this type of current flowing through the inductor will never goes to zero. And the PWM will produce a periodic switching. That means we have the PWM with a specific period to control the switching behavior of the MOSFET. To derive the second equation, we will see that the Kirchhoff current law and the Kirchhoff voltage law plays a very important role in deriving the equation of the buck converter. And if I can define the KCL law, the KCL law states that the total current entering a node is equivalent to the total current leaving the node. So what is a node in this circuit? So this is a node. So if we have I1 passing through this node, and also we have I2 passing through this node, and the output will be I3. So we will see how this equation plays an important role in the derivation of this buck converter. And we can see that now I3, which is the total number of current leaving the node, is equivalent to I1 plus the I2. And this is the basic understanding about a KCL, or the Kirchhoff current law. And the other one is the KVL. So what does this KVL means? So in Kirchhoff voltage law, it says the sum of voltage in a closed loop circuit is equivalent to 0. So in the KVL, we can say that if we have a circuit like this, and if this circuit is a closed loop, that means the voltage in this closed loop circuit will be equivalent to 0. And now we are going to derive the second equation using the KVL and the KCL. To understand the second equation, we will now introduce what is called the state variables. So the state variables in a buck converter is mostly the inductor current, which is denoted by the IL, and the second state variables in a buck converter is the output voltage, and is denoted by V0. Why do we need a state variables? If you look at the state variables, those are the circuit parameters that are mostly changing. So as the buck converter operates, we will see a change in the inductor current and the output voltage. Because of these changes in the state variables, we are going to perform differential equation based on the state variables, because those variables are changing. So it is important that you know why do we need a state variable. In order to put the state variables in order, we will now introduce the state vector. So a state vector can be represented such that x is equals to a vector of V0 and the IL. So this equation becomes more important when we want to model a system based on the next discussion, which is the state space averaging model and the generalized state space averaging model. And having that in mind, We are now going to consider how to derive the equation, and the equation is mostly based on the operation in a continuous conduction mode, where we say that the inductor current cannot go to zero, and the operation of the switch such that the switch will be on and off. So during the on state we will derive the equation, and during the off state we will derive the equation and how we can combine them together. In order to understand in the on state, I will draw the circuit diagram and we can derive the equation. And we have the voltage input such that if we have a DC as a voltage input, and we have the switch, and during the on state we now say that the switch is closed. And when the switch is closed, what will really happen? The inductor will have a connection such that it will conduct, and all this current will be stored inside a capacitor and then will be released to the resistor, and we have the voltage output. So when this is in a on state, that means the switch is closed. So we will have the current which will now flow in this direction to the output. And when it is conduct in that mode, that means this will be reverse bias. That means current cannot flow in this direction. So this becomes an open circuit. And in here we have the positive and the minus, where we have the voltage of the inductor, and we have the IL, which is the current to the inductor. So this now becomes our closed circuit, where this is our capacitor and this is our resistor. And remember that the Vout is the voltage drop across a resistor. Now if we apply a KVL, which is the Kirchhoff voltage law, to the circuit, and since this is a closed loop, we can now derive the equation for this circuit when it is in the on state. And we can say that the Vin will be equals to the VL plus the V0, where this VL is the voltage across the inductor and the Vout is the voltage drop across the resistor, and it is parallel to the capacitor. So that means the voltage across the capacitor and the voltage across the resistor load will be the same because they are connected in parallel. Now since we have the Vin, and when you look at the VL, the voltage across the inductor is such that we have IL, where IL is a current through the inductor that is changing. Now since it is changing, we will take the differential equation of VL, which is corresponding to the differential equation of the current which passes through the inductor, or the change in current through the inductor. Now we have the Vin is equals to L, which is the value of the inductor, and we have DIL on dt plus the V0, which is the output. Now we can transpose this formula such that we have L DIL on dt is now equivalent to minus V0 plus the Vin. So this becomes our equation number 1 through the Kirchhoff voltage law. Now we will apply what is called the KCL law to the circuit, and now we can see that we will have a current that is from this node. We have IL which is coming in, and we have the current to the capacitor, which we can say IC, and we can say IR. And now we can say that IL is equals to IC plus IR. And this is the KCL law from this particular node here. And when we transpose, we now will have IL is equivalent to C dV0 on dt plus V0 over dr. And since the current through the resistor is equivalent to the voltage output over the resistor using the Ohm's law. And now when we put it in a more formal way, we can now see that the C dV naught on dt is now equivalent to IL minus V naught over the R. So this now becomes equation number 2. And these two equation 1 and 2 is from the operation of a buck converter during the on state. Thank you for watching our video. Kindly subscribe to our channel and share this video with your friends so they can also be able to learn